Okay, so let's take a look at the rest of the basic differentiation rules handout. In the previous video, we worked out examples 1 and 2 and the proof of the power rule. There are these other rules, and we've actually already been using them in class. We did some examples with them. But if I give you some function where it's really c times a bunch of x terms, and c is a constant, then when you take the derivative of f, that's what this says, then it's really just the constant times the derivative of the x terms. And then another thing is if I have a function and it's really some x term function plus another x term function, then the way I take that derivative is I just take the derivative of the first guy plus the derivative of the second guy. And so I think these are easier seen in examples than they are seen in the formal notation. But here's p of t right here in example 3, and we're supposed to find dp dt. And remember, this is the same thing as p prime of t. So p prime of t, well, it's a sum of a bunch of mini functions, essentially. It's the sum of this function plus that function plus this function plus that function, or minus the 5/3 t. So really all I have to do is I have to take the derivative of each one. So the derivative of t cubed, using the power rule, is 3t squared. And then the derivative of 6t squared, well, it's a constant times t squared, and the derivative of t squared is 2t to the first, so 2t. When I take the derivative of negative 5/3 t, well, just think of it, it's if I said, what's the slope of negative 5/3 t? Well, it's negative 5/3. And then you're done with that. And if I said, what's the slope of a constant, 16, well, 16 is a flat line that looks like this on a graph. So that's plus 0 right there, because its slope is 0. The slope of any horizontal line is 0. So then if I simplify this a little bit more, 3t squared plus 12t minus 5/3, and then we're done. There's the derivative right there. So let's do one more example, number 4. Find f prime of f if f of x equals this. So f prime, well, actually, let me rewrite f of x using actual single powers here. So it's 6x to the 4th minus 3, and then x squared in the denominator is like x to the negative 2. And then 4 root x is like 4x to the 1/2, where just the x is to the half. So then when I want to take the derivative of this guy, I'm going to use those rules that I just came up with. So the first one, 6 is a constant, so then I'm just going to multiply it by the derivative of x to the 4th, which is 4x cubed. And then minus 3 is a constant, and x to the negative 2 becomes negative 2x to the negative 2 minus 1, so negative 3, using the power rule. And then the last term is 4, and then the x to the half becomes 1/2 x, and then I subtract 1 from 1/2, and I get negative 1/2. And so then we'll clean that up just a little bit. We get 24x cubed plus 6x to the negative 3, which is 6 over x cubed, and then plus 4 times a half is 2, and then the x to the negative half is like over root x right there. So there's f prime. Right. Let's just go ahead and crank out the last couple examples while we're doing it. So example 5 is find all the places on the curve where that function has a horizontal tangent. So remember, horizontal tangent, that means the same thing as slope is 0. So and slope is the same thing as f prime or dy dx equals 0 in this case. So, and you can also say y prime if you wanted to, or dy dx. So we want this to equal 0. Okay, so let's find dy dx. So dy dx, that's the slope of y. Well, using the power rule and all those other rules that we just figured out, that's going to be the derivative of x to the 4th, which is 4x cubed, minus 2 times the derivative of x squared, which is 2x, and then the derivative of 2, that's just a flat line, so that's plus 0. So then if I work this out a little bit more, dy dx equals 4x cubed minus 4x. Whoops, that's a cube. Okay, and remember, we want this to be 0 to get the horizontal tangent. So if I set this equal to 0, then I can factor out a 4x, and I get x squared minus 1 equals 0. And then I can factor this a little bit more, x plus 1, x minus 1 equals 0. And then I can say, okay, so x equals 0, x equals 1, or x equals negative 1. Really, this one's a negative 1 in the middle. And x equals 1. So these are my places when I get a slope of 0. So let's take a look at the points on the actual curve. So when x is 0, y is going to be, so let's say, here, let me write this out. If x equals 0, then y equals 0 to the 4th minus 2 times 0 squared plus 2. So that's 2. So then I know at the point 0, 2, I get a horizontal tangent. If x equals negative 1, then y equals, let's see, negative 1 to the 4th, which is 1, minus 2 times negative 1 squared plus 2. These guys cancel, so I'm left with 1. So then I know I get a horizontal tangent at negative 1, 1. And then if x equals, what's the other one? 1. Then I get y equals 1 to the 4th minus 2 times 1 squared plus 2. And that also equals 1. So then I know that I have a horizontal tangent at the point 1, 1 as well. So there's the answer to number 5. And then number 6 is a physics-related problem. So 6 says, let the position s in meters of some particle moving around at time t in seconds. Let that position be given by this function. So s of t is the position function. And it asks us about acceleration and velocity. So, and the position is in meters. Now remember, velocity is the slope of position. So it's really s prime of t. And this is going to be it, and that's velocity. And that's in meters per second. And then there's another term, and we've mentioned this briefly in class, but acceleration is actually if you go one more step. So that would be the slope of velocity, or you could say it's the second derivative of position. So that's what acceleration is. Acceleration. And acceleration, if you said, well, like if we took a velocity graph, then the y values are in meters per second, and the x values are in seconds, or the t values are in seconds. So if I said take a slope, you'd have meters per second, and that's the same thing as meters per second squared. It's how fast your velocity is changing per second. So let's see, we need to figure out when the velocity is 0 and then figure out the acceleration at each one of those times. So let's look at the position function again. So s of t equals t cubed minus 6t squared plus 9t. And so if I wanted to figure out the velocity, I'm going to take the derivative of s. So using the rules that we just came up with, t cubed turns into 3t squared, minus 6, and then t squared turns into 2t. And then the slope of 9t is just 9. And so then let me just write v of t here. That's going to end up being 3t squared minus 12t plus 9. And I care about when the velocity is 0. So let's set this equal to 0, right? So I could divide everything by 3, and if I do that, I get t squared minus 4t plus 3. And this factors nicely into t minus 3, t minus 1. So the times that the velocity are 0, velocity equals 0 at t equals 3 and t equals 1 in seconds. Okay, so what I wanted to do is figure out the acceleration at those times. So we need the acceleration function. And that is the slope of the velocity function, or the second derivative of the position function. And so v of t is right here. So if I take the, or actually right here, let's say. So if I take the derivative of this guy right here, then I'm going to get 3 times the derivative of t squared, so that's 2t, minus the derivative of negative 12t, which is just negative 12, and then the derivative of 9, which is 0. So then I've got 6t minus 12 is my acceleration function. And I wanted the acceleration when t was 3 and when t was 1. So at 3 seconds, the acceleration is 6 times 3 minus 12, which is 18 minus 12, which is 6 meters per second squared. Well, so this is at t equals 3 seconds. And then a1, acceleration at time 1, is 6 times 1 minus 12, which is negative 6 meters per second squared. Okay, and I hope that helps a little bit. If you're having trouble conceptually understanding what acceleration is, we can talk about that in class. I realize this, like, for now, as long as you understand acceleration is the derivative of velocity and velocity is the derivative of position, then at least you can do the work that you need to do for this. And then conceptually, we'll talk about like why this works the way that it does in class. Okay, I hope that helps a little bit, and I'll see you guys soon.